This video is for lesson 3-1 about geometric definitions and two-column proofs. This is the first lesson in activity 3, which is about the axiomatic system of geometry. Learning targets are to distinguish between undefined and defined terms and to use properties to complete algebraic two-column proofs. So even though we're a geometry class, our first practice in proofs will be with algebra problems because you are more familiar with algebra. Geometry is an axiomatic system. That means that the ideas of geometry are based on axioms. Axioms are a small set of agreed upon assumptions. From this small set of beginning assumptions, all other ideas in geometry are created using logical reasoning called deductive reasoning. In geometry, it's necessary to agree on clear-cut meanings or definitions for our words. For a definition to be helpful, it must be expressed in words whose meanings are already known and understood. To be helpful, vocabulary words need to be defined using words that have already been defined. But there always has to be a few first words that can't be defined. In geometry class, these are called undefined terms, and there are just a few of them: point, line, and plane. Remember that you learned to draw and name these in an earlier section. From these three undefined words that we only have an understanding of because we're able to draw them, we can define other words like ray, collinear points, or coplanar points. Number 2, define these terms using the words up here. These words might be defined like this. A ray is part of a line bounded by one endpoint. Notice that in the definition of the word ray, that the word ray is right at the beginning of the sentence to be the subject of the sentence. And then later on, when defining a ray, we use the word line and even the word end point. Collinear points are points that lie on the same line. So again, in this definition, collinear points is the subject of the sentence and written at the very beginning. And then later on in defining that, we use the word point and then even the word line. Coplanar points are points that lie on the same plane. I'm going to pause the video here so that you can record these definitions so that you can use them on your assignment later. After a term has been defined, it can be used to define other terms. For example, an angle is defined as a figure formed by two rays with a common endpoint. So just a little bit ago, we defined the word ray, and now we can use the word ray in our definition of the word angle. We just keep building more and more defined words in geometry, and that's why it's called an axiomatic system, where ideas are built on the ideas that have been created before. Number 3, define each term using already defined terms. And here are the definitions. Complementary angles are two angles whose measures sum to 90 degrees. Supplementary angles are two angles whose measures sum to 180 degrees. Hopefully you recall that these two concepts were on your first quiz this year. I'm going to pause the video here so that you can copy these definitions for your use later. The process of deductive reasoning must have a starting point. A conclusion based on deduction can't be made unless there is an established assertion to work from. To provide a starting point for the process of deduction, a number of assertions are accepted as true without proof. When you solved algebra equations in algebra class, you used deduction. You used properties to support your reasoning without having to prove that the properties were true. Someone else showed that those properties were true, and then they were put in your algebra book for your use. And then you solved equations to find an answer for x. Number 4, use one operation or property per step and show how to solve the equation 4x plus 9 equals 18 minus 1/2 x. Name each operation or property used to justify the steps. The operations and properties that we have to choose from are over on the side of the page. To solve this equation in algebra class, the first thing that you probably did was write it out. And here it is. Notice on the left side of the equation is the expression 4x plus 9. On the right side of the equation is the expression 18 minus 1/2 x. When solving an equation, we want to get the variable on the left side of the equals. So let's make the 1/2 x term move to the left side of the equation. Under here, we can add 1/2 x. And that's allowed as long as on the other side of the equation you also add 1/2 x to keep the equation in balance. 4x plus 1/2 x is 4.5 x. There's still a plus 9 and an equals and an 18. But by adding 1/2 x underneath the minus 1/2 x, this term canceled away out of the equation. This question asked us to name the operation or property we used as justification for each step. When solving this problem, we said, hey, let's add 1/2 x to both sides of the equation. Why is that okay to do? Looking over on the left side of the screen, that's the addition property of equality, which says that if you add the same thing to both sides of an equation, that doesn't change the value of the equation. So if we're going to provide a justification for creating this new equation, our justification is called the addition property of equality. Some algebra teachers, when they're teaching students to solve equations, required the students to write down reasons every step of the way along the equation, but then some teachers didn't do that. Okay, let's go back to solving the equation. In solving the equation, we want to collect the x term on the left side of the equals, but put any constant terms to the right side of the equals. Underneath the plus 9, let's subtract 9, which is okay as long as on the other side of the equation, you also subtract 9 to keep things in balance. That will create 4.5 x equals 9. The plus 9 and the minus 9 cancel away. Now, why is it okay to subtract 9 from both sides of an equation? And over on the left side of the screen, we see that that is the subtraction property of equality. So if we're going to write a justification for writing this equation, 4.5 x equals 9, our reason is because of the subtraction property of equality. We don't quite have the x alone. There's one more step to go. We can remove the coefficient in front of x using division. Let's divide by 4.5. And over on the other side of the equation, divide by 4.5. This creates 1x, or simply x, equals, and 9 divided by 4.5 is 2. What is the reason that we can divide both sides of an equation by the same number? That is called the division property of equality. We have solved the equation because we've written the equation so that the variable is all by itself, and that's what it means to solve the equation. We found out that x is equal to 2. And we've justified each algebra step with a reason why the step is legal. In geometry class, we can organize our steps and our reasons used to justify the steps into 2 columns. The first column will contain statements, which are our steps of work, and the second column will contain our reasons, which are our justifications for the steps. This format is called a 2-column proof. Take a quick look here at example A. Let's say that we had this algebra equation. This is a pretty complicated equation. It would take a few steps to solve it. And we want to prove that the answer is x equals -3. In algebra class, you would write out the equation and then step by step work your way down until you got to the answer x equals -3. A 2-column proof is identical to that work that you did in algebra, but over here on the right side, we're writing justifications for each step. So when we first copy the equation down, our justification for writing that is that that is our given equation. When we get from the first step to the second step, notice what happened. It looks like that 1 was added to both sides. That's how this became 12. Our justification for creating this equation in line 2 is because of the addition property of equality. That is the reason why we can add 1 to both sides. What is the justification for writing what's in line 3? Well, it looks like the distributive property was done to create 3x plus 6, and so we write down distributive property as the reason. Now, going from line 3 to 4, what happened? Well, how did this become 2x? Looks like that the 3x was subtracted from both sides, so our justification is the subtraction property. Going from line 4 to 5, can you tell what happened? It looks like that this 12 was removed using subtraction. Why can you subtract 12 on both sides? Because of the subtraction property. Step 6, where did this come from? What was done to what was there before? Looks like we divided by 2 on both sides, and so our justification is the division property. And finally, in algebra, what is the reason you can say that negative 3 is equal to x could be rewritten as x equals negative 3? Why is that okay? Because of the symmetric property of equality. So this thing here is called a 2-column proof. And it's a 2-column proof about an algebra problem. Later in geometry, we're going to write 2-column proofs for geometry problems. Okay, now we have a try this problem, and I'm going to pause the video here for you to work on this. Think about what would be the reason that you would put in each of the blanks here in the right column to justify these statements that are in the left column. Here's the solution to the try this. This first equation is simply the one that was given to us, and so our reason is given. In fact, almost every proof you do, your very first reason will be to copy down some given information. Okay, to figure out the justification for line 2, we have to look to see what has happened compared to what we had previously. It looks like that the number 10 was multiplied to both sides of the previous equation. So that's the multiplication property of equality. To figure out the justification in line 3, you have to figure out what happened from line 2 to get to line 3. Where did the 5 come from? Where did the 2 come from? It looks like that the 10 over 2 was replaced with 5 because 10 over 2 is just 5. Over here, the 10 over the 5 like cross-canceled and made the 2. This is called substitution, when you replace an algebra expression with something else that's equal to it. Okay, line 4. To get from the previous equation to what's in line 4, it looks like the distributive property was done. So this one is distributive property. I'm going to abbreviate that. Okay, line 5, what happened? To get 3x here, what happened? It looks like we used the subtraction property. Okay, line 6, looks like the 15 was added to the 12, creating 27, so we must have used the addition property. And finally, in step 7, how do you get x equals 9? We had to use the division property. This entire thing is called a 2-column proof. Here are some check your understanding questions. I'm going to pause the video for you to work on these. Here's the answer for 5. Explain why undefined terms are necessary in geometry. There have to be a few undefined words at the beginning for us to create other definitions using those words. Number 6. What is the relationship between conjecture, theorem, and 2-column proof? One way to answer is to say a 2-column proof is used to change a conjecture into a theorem. A conjecture is our best guess based on the observations we've made from patterns or cases. If we prove that that guess is true, it becomes a theorem. Number 7, Jeffrey wrote a 2-column proof to solve the equation 3 times x plus 5 equals negative 6x plus 6. In addition to incorrectly writing the prove part of the statement, what error did Jeffrey make in his proof? Let's rewrite it to fix this. So he first copied the equation down, and let's check to make sure that he copied it accurately. Yes, he did. And he gave the reason given. That is correct. Next step, it looks like he did the distributive property to get 3x plus 15. Then he has this copy correctly, and he said distributive property. That is correct. Next step, it looks like he added 6x to both sides. 3x plus 6x is 9x, and this canceled away. This is correct, and he said addition property. It's right so far. Next, how did he get from line 3 to 4? Looks like he wanted to subtract 15 from both sides to remove the 15. 6 minus 15 is negative 9. This is correct, and he did subtraction, and he said subtraction. Everything's good so far. Next step, he wanted to get the x alone, so to remove the coefficient requires dividing by the 9 on both sides. Negative 9 divided by 9 is not negative 81. There's the mistake. This is negative 1. And it's not multiplication, it is the division property of equality. So the proof is fixed. In this lesson, we discussed undefined terms. They were point, line, and plane, and defined terms, which are all the additional words we're going to use in geometry. And we used properties to complete some algebra 2-column proofs.